Welcome to this explainer. Listen, if you are sitting the Cambridge Computer Science exams, especially that notoriously tough 9618 syllabus, you are basically stepping into an exam wasteland. It's a place where marks are fiercely fought for and incredibly easy to lose. Whether you are building your foundation with syllabus codes 0417, 0478, 0983, 0984, 2210, or you're tackling the heavy-duty 9618 A-level, the struggle is real. Today, we're zooming in on a deceptively simple topic that becomes a massive trap for so many students, the declaration and initialization of constants. Picture two specific students in the exam hall right now. Let's call them Alex and Sam. Alex completely overloads his answer with raw, memorized computer science facts, dumping everything he knows onto the page without a shred of actual analysis. Then you have Sam. Sam rushes the paper, totally missing the specific command word requirements like evaluate or describe. What happens? Both of them lose critical marks instantly. They leave easy points on the table. But today, we are going to transform you from an exam wanderer into a top-scoring veteran by analyzing their mistakes and giving you a bulletproof strategy.
Okay, so here is our strategic map for today's session. We'll start by navigating the exam wasteland. Then we'll move into mastering your core principles. After that, we'll unlock what I call the method mark strategy, followed by a breakdown of the technical execution framework. We'll wrap things up by looking at the top examiner warnings and finally, a critical analysis masterclass. Let's dive right in.
Section 1, the exam wasteland, and how to navigate those unbelievably tricky questions that Cambridge loves to throw at you.
Now, you might be wondering, why do most students walk into the exam hall completely without a strategy? They assume that constants like constants are just dictionary definitions to be memorized. But here is the exact question senior examiners are asking. Why do students find applying concepts to unfamiliar contexts so incredibly hard? Think about it. Learning the basic syntax to declare a constant takes, maybe 5 seconds? You type it out and you're done. But understanding its actual computational implications within a broader system? That takes deep cognitive processing. We're talking about how a constant affects memory management, how it prevents catastrophic hard coding errors, or how it's used to reliably extract binary data. When faced with a brand new context in an exam, panic sets in, and candidates completely fail to see how a simple constant is actually the anchor for the entire logic of their code.
Just look at the distinct contrast here. On the left side, we have our doomed survivor, kind of like our friend Alex from earlier. They provide super vague details and completely ignore edge cases. If the paper asks them to initialize a constant for an array boundary, they just write constant max equals 10 and move on. They don't link it to the data structure at all. But on the right side, we have the top-scoring veteran. They provide highly specific technical details. They use a structured approach like the PEEL framework, point, evidence, explanation, link. They make their point, provide the technical evidence, explain the mechanism, and link it right back to the specific scenario. They actively test boundary conditions, proving to the examiner exactly why a constant protects the algorithm from, say, an overflow error later down the line. They truly understand the core computational purpose behind the code. Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
All right, moving on to Section 2, Mastering Core Principles. This is essentially building your ultimate survival toolkit. To actually survive and thrive in these exams, we desperately need to decode the examiner's assessment objectives. We're talking about knowledge, application, and analysis. And the absolute bedrock of this is what we call theoretical architecture. Listen, you cannot learn computer science in isolation. It's not a bunch of disconnected facts. It's a web. For example, when you declare a constant, how does that specific choice impact the space complexity of your algorithm? How does it interact with the specific data types being processed? Top-performing students exhibit this connected, conceptual understanding. Because they understand the architecture, their knowledge transfers effortlessly to those tricky, unfamiliar contexts the examiners love to use to trip you up.
To really lock this architecture into your brain, I want you to try this incredibly powerful visual memory hack. Next time you're studying, visualize your code as a physical, fortified castle. A declared constant isn't just a line of text on a screen. Visualize it as a massive, unbreakable iron vault being dropped right into the center of your fortress. Initializing it, that's you setting the unbreakable lock code on that vault door. By visualizing edge cases as literal attackers trying to breach the walls of this vault, you instantly train your brain to anticipate boundary condition errors before you even write your test data. It's a total game changer.
Section 3, let's talk about the method mark strategy. This is where you gather the treasure, even when things go slightly wrong.
I need you to read this direct quote from a principal examiner alert because it is your absolute ultimate safety net. Quote, "Students lose marks by not showing working. Even if your final answer is wrong, method marks can save you." End quote. Let that sink in. The examiner actually wants to give you marks. If your final algorithm crashes because of a minor syntax error, maybe you missed a semicolon or flipped a greater than sign, but you clearly showed your step-by-step logic and your clear, purposeful, constant declarations, the examiner will reward that procedural working. You are proving your analytical depth over superficial breadth, and that is what gets you the A star.
Stop scrolling. Subscribe to our YouTube channel Ace the Exams at Ace the Exams IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @Ace the Exams IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Okay, let's jump into Section 4, the Technical Execution Framework. These are the survival mechanics you need to deploy.
True algorithmic thinking requires strict, uncompromising adherence to these 4 steps. First up, step-by-step decomposition. You have to break the massive, terrifying problem into manageable logic gates. Don't try to swallow the elephant whole. Second, appropriate data structure selection. You've got to choose the right tool for the job. Is it a 1D array, a 2D array, a linked list? Third is efficient code implementation. This is exactly where your perfectly initialized constants come into play to maintain total code stability throughout the program's execution. And fourth, rigorous testing. Here's a golden rule. If you can't decompose the problem in the first 60 seconds of reading the prompt, step back. Do not write anything. Reread the command words before you write a single line of code.
Let's test this right now with a mental data scan challenge. Imagine a complex data table on your exam paper. You have 60 seconds on the clock. A true veteran doesn't just stare blankly at the numbers. They instantly deploy these crucial data interpretation skills. They scan and extract the core trend from the binary representations. They perform accurate calculations on the fly, and they draw immediate, evidence-based conclusions. If you decide to declare a constant limit for a binary shift operation, you must have calculated exactly why that specific limit is required by the hardware described in the question. This level of precise interpretation isn't optional. It's strictly required for top marks.
Moving into Section 5. This is crucial. These are the top examiner warnings. This is how we avoid the traps that destroy so many grades.
It's challenge time again. Let's play Find the Flaw. Imagine a student writes an algorithm to process an array of exactly 100 student grades. They write a loop that says, while count is less than 100. I want you to mentally scan that. Can you spot the missing boundary condition? I'll give you a second to think about it. Okay, time's up. The massive flaw here is that depending entirely on how they initialized their count variable, did it start at 0 or 1, they might only process 99 items, or worse, they might crash the entire program trying to access index 100, which doesn't exist. This is the exact kind of edge case oversight that completely tanks your grade.
Let's break down the top 3 fatal mistakes pulled directly from the principal examiner reports. Number 1. Answers on declaration and initialization are often way too vague. Examiners demand specific technical details. Do not just write, "It makes the code better." That's 0 marks. You have to explain exactly how it optimizes memory allocation or prevents accidental hard-coding errors. Number 2. Forgetting to check boundary conditions and edge cases, exactly like the flaw we just found with that while loop. And number 3, answers are not specific to the context. If the question is about a self-driving car's proximity sensor, your constant shouldn't be a generic X or limit, it should be something highly specific like constant max_sensor_range. Context is king.
Finally, Section 6, the Critical Analysis Masterclass. This is where we evaluate the terrain and secure that A star.
To truly step into the role of a software engineer, you must absolutely master the deconstruct, solve, evaluate cycle. This is the blueprint used by the absolute highest scoring candidates. Step 1, identify the given information. Step 2, break it into logical steps. Step 3, solve systematically, showing all your working so you can scoop up those beautiful method marks we talked about earlier. Step 4, check for reasonableness. Seriously, if your calculated array size is a negative number, you've clearly made a mistake. Catch it before the examiner does. Step 5, make justified recommendations. This entire cycle is powered by logical reasoning and incredibly strict time management.
When you are making those recommendations, examiners demand specific evaluative metrics. You must analyze the trade-offs. You have to analyze time complexity, literally. How fast does this algorithm run? You must analyze space complexity. How much memory is this thing going to consume? And finally, you must identify edge cases and explicitly state their exact effect on the system's performance. You have to acknowledge limitations and justify every single algorithmic decision with hard, technical evidence. Listen, students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos.
So, armed with the method mark strategy, your new visual memory hacks, and a precise understanding of technical context, the exam wasteland is now yours to conquer. Remember, every single constant you declare and every variable you initialize is a deliberate, powerful architectural choice. So, the next time you sit down with a blank piece of paper, a tricky scenario, and a ticking clock, how will you engineer your next solution to survive the examiner's scrutiny? Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.